Assalamualaikum and selamat sejahtera. I am Kamarul Imran Musa, but please call me Kim. I'm a professor in epidemiology and statistics at the School of Medical Sciences, Universiti Sains, Malaysia. And I would like to welcome everyone to our online seminar today. So the seminar is co-organized by the Unit Science Kesihatan Digital or Digital Health Sciences Unit and the Digital Health and Profession Research Cluster at the School of Medical Sciences, where I am the coordinator for the unit and also for the research cluster. So we are here today to listen to a very interesting talk entitled Time Series Forecasting with R, Some Theory and Applications. And with us today is my good friend, Associate Professor Dr. Jason Ng. And he is an Associate Professor at Sunway University, specializing in econometrics and data science. His research interests involve subjective well-being, Malaysian housing affordability, vulnerable communities, and electorate behavior dynamics modeling. I am honored to have co-author a few papers with Jason. He is, a very, very intelligent person, I would say. He's a dedicated educator, and he integrates R, a widely used statistical tool, into his teaching and research. And he, with a certification in data analytics, he aims to shape evidence-based policy for societal advancement. Right. All right. A little bit of background noise. So I hope to remind everyone to mute your mic. And Jason earned his Bachelor of Commerce honors and PhD from Monash University, Australia. So we are grateful that Dr. Jason has agreed to deliver this talk. Again, the title of the talk is Time Series Forecasting, Some Theory and Applications. So I think without further ado, we have until 2:30, 3:30, 3:40. So let me invite Dr. Jason to the center stage and deliver your talk. Jason?
Yeah. All right. Thanks, Kim, for inviting me here. And a very good afternoon to everyone here. Thank you for making time for this. Firstly, I've got to apologize for my voice. I kind of lost my voice on Sunday, so I've only recovered about maybe 75% of it. So it sounds like it sounds like a frog. I don't like how I sound, but we shall see how it goes. All right. So I was invited by Professor Kamarul to give a talk on time series forecasting using R. And I understand that most of the attendees here are probably from medical science background, and therefore most of you might not have much experience with time series data. So this 1 hour and 15 minutes is really a crash course, going to bring you through 90 minutes or about 75 minutes of stuff that I'll normally cover in about 13 weeks. All right, so just to manage expectations a little bit, we'll be really touch and go. So my name is Jason. I'm the Deputy Dean at School of Medical Sciences. I'm also heading the Center for Actuarial Analytics Research. So this is the list of topics that we'll be covering. So sections 1 to 5 is really for me to cover the groundwork. What are some of the concepts related to time series? And then from section 6 to 11, I'll be introducing some of the very common forecasting methods and models. And then sections 12 and 13 is really for us to discuss, we go through so many possible forecasting methods, right, and models. Which one should we choose? And it really boils down to choosing the one which gives us the best forecast accuracy. And there are two approaches in terms of how we actually evaluate such a forecast accuracy. All right, so let's go into it. So starting definition, again, assume that, most of us might not be familiar with time series. You have basically observations on a particular variable over time, all right? And it's usually at regular intervals, and I will only keep my discussion to regularly timed intervals for time series data. We need to recognize that such time series variables, they are actually random variables, all right? And we denote them by the subscript YT. And it's only when we observe a particular value for that variable, then we say that a realization of that time series has happened. All right, so we will use YT to actually denote the random variable. So it's a random variable when the value has not yet been realized. And when you actually observe the value, that YT is no longer a random variable, we say that a realization has happened. Now, time series data is actually very common. In Malaysia, and I think if you look at the open data set, the Ministry of Health open data set, so this is the KKM now, all right, I'm using this because I believe that most of you here are medical professionals. If you click on, let's say, hospital bed utilization, all this is time series data because it's data tracked over time. I think if you talk about blood donations, if you look at daily, you can actually see a seasonal pattern here, but it's pretty much stagnant as well. You can click monthly data or you can click on yearly data as well. So even in the medical health sector, we do have time series data available to us. Okay, so that's a definition of time series data. So we are going to use the notation YT, all right, to denote the value of the time series in time period T, and then we use cat T to denote the sample size. So some properties of such data, there's a particular ordering. So there's no such thing as a random sample that we might be very accustomed to when we're dealing with cross-sectional data. All right, there's natural ordering YT minus 1 precedes YT and YT precedes YT plus 1. And one of the most important things about time series data is they actually have what we call a temporal dependence, or you might know that as correlation. All right, so observations corresponding to different time periods, they're often correlated. So for example, if it's very hot today, you can expect tomorrow to be hot, and you can expect the day after tomorrow to be very hot. Or if you have a very heavy rain today, you can expect tomorrow to have a heavy rain as well. And therefore, because of this sort of temporal dependence, it is not really feasible for us to assume that the random variables YT and YT minus J are independently and identically distributed because of this temporal dependence. All right. Now, it's very important that we are able to visualize our data. So I'm just going to introduce 3 very quick tools in terms of how we actually plot our data. So we can use the auto plot function. So basically, I'm using the FPP2 package in R. All right. And it will automatically download other packages such as the forecast package, the ggplot2 package, and the dplyr package as well, because you can actually use the type operator functions as well. So I'm using this data set called A10 that corresponds to anti-diabetic drug sales. And you can see the plot. All right, so 1992 to 2008. It's very important for us to actually understand how your data is behaving, because when we talk about forecasting, we use statistical models. And such models should actually capture the behavior that you see in a time series. And such visualization plots allow us to know what behaviors are present. One of the analogies that I usually like to give is, we like to go shopping for clothes, right? You need to know your body shape. Are you tall? Are you short? Do you have long arms? Is your waist slim, or is your waist a little bit, thicker? Then that's only when you're able to find clothes that fit you. All right. And the same thing here. You need to know how your data behaves in order to find appropriate statistical models that fit the data well. So you can actually see for this particular data set, you have a trend, and it's a non-linear trend, right? There's a slight curvature up, it's non-linear. You can see seasonal patterns. All right, you can see these peaks and troughs that repeats itself after regular intervals of time. And notice that the seasonal pattern, you can see that, the seasonal variation is actually increasing over time as well. All right, so these are some of the behaviors that we need to be very mindful of when you start using or selecting statistical models to produce forecasts. All right, seasonal plots. This is the same data set A10, but basically it plots the data against the seasons. All right, so this is seasonal data. So you notice that your x-axis here are the seasons of the year. So you have 12 months, and basically each line corresponds to a particular year. So if you see this orange line, You have 1992 January, 1992 February, 1992 March, and you see the time series just stack on top of one another from 1992 to 2008. So you can clearly see seasonal patterns whereby you notice that January always has the highest observation, and then it drops down to February, and then it slowly climbs up all the way to December. All right, so this is some of the things that we should be mindful of. And sub-series plots is basically collecting data for each season and plotting them in mini time plots. So this data is from 1992 to about 2008. So what we have here is that this first point corresponds to January 1992, and this very last point here corresponds to January 2008. All right, it's basically taking the data for each season and producing a mini time plot for each of them. These horizontal lines that you see are the average values. So you can see that January has the highest value, February has the lowest average value, and December has the second highest average value. So you can see that year on year, the amount of drug sales is increasing year on year for each of the months. Okay, so to do this in R is actually quite straightforward. I'm using R Markdown. So the codes that you see in the slides are basically in my R Markdown. So you can just do auto plot A10, all right? That just gives you the raw plot without the labels. All right, make sure that you load the FPP2 package first. All right, so A10 is just basically the data set that's embedded within the FPP2 package itself. So this is the data that we saw, but if you add the various labels, then you get the correct x-axis, y-axis, and the titles. All right, GG season plot. Year.labels is basically I want my year labels to appear on the right, and this argument says I want the year labels to appear on the left, and these are just the y-axis labels and the title for the plot. Okay, and this is what you saw in the slides, and sub-series. All right, so data visualization and time series is actually quite easy to use, quite easy to produce using the FPP2 package. So visualization is just for us to really understand the behavior of the data set that helps us make an informed choice of what statistical models we should be using to do our forecasting. All right, now I'm going to go through some notational conventions because we'll be coming back to them in the later part of the talk. So you're going to hear me talk about the legs of Y, all right, and we denote that by YT minus J. So YT minus 1 is the first leg of Y, YT minus 2 is the second leg of Y, all right. Observation of Y 1 period ago, 2 periods ago. Now, the first difference is really what we call, you might be familiar, the change of Y is just because of Y prime T, which is just a change, which is just YT minus 1. All right, all these notations, we'll be coming back to them later on when we talk about ARIMA models. All right, another notation, so this is how a time series variable, a time series table will look like. All right, this will be your raw data. This would be your column of observations, and this is if you lag your time periods by 1. This is the Y prime T, the first difference, and this is YT lag by 2 time periods. So notice that each of them are columns, so they are actually random variables. All right, each of them, you can consider them as a random variable. They take on different values at different time points. Now, I'm going to introduce what we call a backshift notation at this point. We'll be coming back to it when we talk about ARIMA models later. So I use the notation B. Some textbooks use the notation L. In this case, I'll just use B. So basically, it has the effect of shifting YT back by 1 time period. All right, every B operator shifts YT back by 1 time period. So if I have B squared, it means it shifts it back by 2 time periods. If I use B raised by power 12, it means I'm shifting YT back by 12 periods. So if I'm using monthly data, BY12, which corresponds to YT minus 12, is basically the same month of last year. Okay, so I'll be coming back to the backshift notation because this is what we actually use in ARIMA models. All right, some of you might be familiar with ARIMA, PDQ, and Cat P, Cat D, Cat Q. All right, the way we write this ARIMA is written in backshift notation. All right, so I just thought I'll bring it up here just to cover all our bases first. Okay, so it's convenient for the process of differencing. Again, if you go back to the first difference, YT minus 1 can be represented as 1 minus B times YT, right? You can just take YT as a common factor. Okay, so these will come in handy later. Okay, now what can we forecast? All right, I think we should be quite practical about what can be forecast. This slide actually just shows how forecasting is actually very difficult. This is actually a timeline of very bad predictions that we made. All right, over here, some says that, aeroplanes cannot fly. No such thing as a flying object. This one says there's no reason for computers to exist at home. This one says that, online newspapers will never overtake your daily newspapers. So on and so forth. So forecasting is very difficult. Now, I have a list of, scenarios here, which is the easiest to forecast. All right, electricity demand in 3 days' time, timing of the next comet, the time of sunrise today, but next year, the Google stock price tomorrow, or in 6 months' time, or the temperature tomorrow, or the exchange rate next week, which is easiest to forecast. And we need to know how do we measure easiest and what actually makes something easy or difficult to forecast. And I think this is something that we need to be very mindful of before we embark on any forecasting exercise. In terms of, is it really practical to forecast a particular variable that you might be interested in forecasting? So something's easier to forecast if you have a good understanding of the factors that contribute to it, if you have lots of data available, and the forecast cannot affect the thing we are trying to forecast. So a very famous example is this. If you forecast exchange rates, and you forecast that, let's say the ringgit is going to depreciate against the US dollar. All right, let's say, someone did a forecast of the exchange rate. They say that, the ringgit is going to depreciate against the US dollar. What happens is you're going to create what we call a self-fulfilling prophecy. All right, because when we hear the news, the ringgit is going to depreciate, I better get rid of my ringgit denominated assets. And what happens is when you start selling these assets, then you actually create a scenario where you actually cause the ringgit to depreciate. All right. So it should not affect the thing you're trying to forecast. Something's easy to forecast if there's relatively low on natural or unexplained random variation, and if a future is somewhat similar to the past. All right. I think this is something that we should be mindful of. So some people think that forecasts are not possible, but really, a good forecasting model actually captures the way things move. All right. What is actually assumed is the way the environment is changing will continue into the future, which means if your data has a lot of volatility, then your forecasts will reflect that high volatility. If your data set has very low volatility, then your forecast will also show low volatility. It's very rare whereby if your data shows very low volatility, your forecast will have high volatility and vice versa. All right. That's why when COVID hit, all predictions got wrong. All right. Yeah. All right. So this is forecasting process. It's really 8 steps. First, you need to define what the goal is. You then need to get the data set to achieve that goal, explore and visualize the data set, pre-process the data. All right. Are there any missing observations or are there outliers? And then you've got to do partitioning of series, all right, to help evaluate your forecast methods. Then you apply the forecasting methods, evaluate them, and then implement the forecast. For today, we are really just going to focus on number 6, applying the forecasting methods. I'll only talk a very little bit about number 5 and number 7. The focus today will be really about on number 6. All right, stationary time series. Let me go through very quickly what this means. All right, so this is the mathematical definition of what a stationary time series is. Practically, it means 3 things. You have a constant mean, right? The mean of the time series is constant across time. The variance is constant across time, which means it doesn't change over time. And the covariance or the correlation really depends on the time interval separating them and not on time itself. Therefore, the covariance of Y1 and Y10 is just the same as the covariance of Y21 and Y30, which is the same as the covariance of Y100 and Y110. Notice that each of them had different time periods. This is time period 1, this is time period 10, this is time period 21, time period 30. But notice that for each of the difference, J equals to 9. All right, there are 9 time periods separating them. So these 3 covariances are the same. All right, so the whole idea of stationary time series is it helps us fit a very stable model. All right, everything is under control. All right, if you have non-stationary time series and you try to forecast a non-stationary time series, you're going to have big troubles, difficulties in doing such forecasts because nothing is stationary. All right, things are changing. Your mean is changing over time. Your variance is changing over time. Your covariance is also changing. So it's always better to try to see if you can make your data as stationary as possible. So here's one example. Is this particular data stationary? So if I were to divide this into, let's say, 6 time blocks. If I just focus on time period here, you can see that the mean is around here. All right, the average of series is around here. In the second time block, the average is around here. The third time block, the average must be here. This block average is here, the average is here, the average is here. So notice how the mean is actually not constant across time. It is actually changing. So this is not a stationary time series. Recall that I require all 3 conditions to hold for a series to be deemed as stationary. Mean is constant, variance is constant, covariance is dependent just on J and not on T. So this is not a stationary time series. Now, this is the first difference of the same data set. This is a stationary time series because notice that if I again divide this into 6 time blocks, you can notice that the mean is actually constant. It's just basically 0. All right, and the variance is pretty much constant as well. No doubt that there are some observations that seem to jut out, but overall it seems that my variance is relatively constant. So this is quite a stationary time series. Okay, now again, stationarity is going to be a very big concept when we discuss about ARIMA models later on. Okay, important concept, autocorrelation and partial autocorrelation. So these are the 2 tools that are commonly used to assess the extent of temporal dependence in the time series, and they are useful in identifying possible ARIMA time series models. So what you might have heard this concept, autocorrelation, what is it? Now what we have here is a matrix of scatter plots. All right, you notice that I've got leg 1, leg 2, leg 3, leg 4, all the way to leg 12. And all these dots that you see here, those are the actual observations we have. So each graph actually shows YT plotted against YT minus K. So for each of these plots here, my vertical axis is YT. All right, each of these here is YT. But for this horizontal axis is YT minus 1, this is YT minus 2, and then this is YT minus 3. So you can see the relationship between YT and its legs. And you can see that from this graph, they are all positively correlated because it's trending upwards. But you can see that, especially at leg 12, the scatter plots are very tight. All right, the points are very tight. So this means that the correlation, the relationship is stronger compared to, let's say, this one where the scatter points are more scattered. All right, they are more dispersed, whereas at leg 12, they are more tightly condensed. So this one has a stronger relationship between YT and YT minus 12. So autocorrelation is basically the numeric measure, the metric associated with these scatter plots. All right, so we have the autocovariance and autocorrelation. They measure the degree of linear relationship between the lag values. All right, this is the formula just for presentation purposes. And we can easily obtain them in R by just using the GGACF function. So what we have here is, this would be the autocorrelation at leg 1, which is the correlation between YT and YT minus 1. This would be the value of the correlation between YT and YT minus 2. This would be the autocorrelation value of YT and YT minus 3. So notice that it is all positive, all right? All the values here are positive. Anything below this axis here is negative. All right, these blue lines that you see, they are the 95% confidence interval. All right, if you have got autocorrelations within that 95% band, it just means that the sample autocorrelation is not significantly different from 0. Notice that at leg 12, my autocorrelation value shot up, which is what we expected because, as I explained in this graph, the scatter points here are more tight. All right, therefore, it indicates a stronger relationship compared to, let's say, at leg 6, where the points are more dispersed and scattered, you will have a weaker relationship. So notice that leg 6, my autocorrelation value here is lower than the autocorrelation at leg 12. So you can easily produce this graph. All right, using the ggacf function, and I just add a title. Okay, got a comment to, hopefully this helps, the font size. Thank you for that comment. Okay, so this is the lag plot. If I want to plot the ACF, just use a ggacf function, and I just get a plot. Now, if you really want to get the actual values in practice, we usually just look at a plot. We don't really get the value. But if you really want to get the value, then just use ggacf, call out the name, $data, $frequency, and you have the values here. All right. So the first value is 0.8, second value is 0.74, so on and so forth. All right. But in practice, we normally just look at a plot. Yeah, we don't really pay too much attention about the actual values here. So this is the sample autocorrelation function, or we call it the ACF. So another concept which is closely related to ACF is what we call the partial autocorrelation. All right, so the partial autocorrelation, which we can denote, using, which we denote using phi jj, is basically a correlation between yt and yt minus j, but we remove the effects of the intermediate values. All right, so that's the concept of partial autocorrelation. It's a correlation between yt and yt minus j, but you partial out or you remove the effects of the intermediate values. All right, so the sample PACF, we can just basically use the ggPACF function and then just call out the data set. So if I go back to my R codes, just use ggPACF. Notice that the P is in uppercase. All right, so R is case sensitive, so make sure that you have an uppercase P. Okay, and you get this plot. All right, so lag 1 is positive, lag 12 is positive, and those sample partial autocorrelations that are within the 95% confidence, it means that they are not significantly different from 0. Okay, so these are concepts that we'll be relying heavily on later when we talk about ARIMA models. Okay, the final concept to go through before we look into the forecasting methods, white noise. So white noise basically is quite similar to a stationary time series, whereby you have a 0 and constant mean, a constant variance. But the most important thing about white noise series is there is no correlation at all. All right, so a time series is considered white noise if there's no autocorrelation. Previously, for stationary time series, we said that the covariance of yt and yt minus j is equals to gamma j, which is not necessarily equals to 0. If it equals to 0, then it's called a white noise process. So a time series white noise if there's 0 mean, constant variance, and no serial correlation. And why is this important? Basically, when you fit any statistical model, right, let's say y equals to f of x plus an error term, how do you know if your model is adequate? Basically, your error term should be a white noise process. And that's where we need to do what we call a diagnostic check. All right, so I'll also go through that, what sort of diagnostic checks that we can do. So this is how a white noise process looks like. Okay, you've got a constant mean of 0 here. The variance is pretty much constant as well. And notice that all the sample autocorrelations here, they are within my 95% confidence interval, meaning that none of these autocorrelations are significantly different from 0, right? All of these autocorrelations, which I denote as rho j, they are all equal to 0. All right, so this is how a white noise time series would look like. Both the ACF and PACF all pretty much equals to 0. All right, and why is white noise important? Because when we feed a forecasting model, you've got to check the residuals. Is this a white noise process? And we need to go through the diagnostic checks. Okay, Now that we've covered all the foundational concepts, let's go straight into the forecasting models. So there are a lot that I need to go through here. So let's look at them. So linear regression models, I think we are quite familiar with that. So I'll skip the slide. So I'm going to illustrate a very simple way as to how I can fit a regression model. All right. And in general, you specify the regression model. That's where you need to actually visualize the data. Notice what behavior or characteristics it's displaying, and then make sure that your regression model is able to account for the particular behavior. Once you specify the model, we estimate the model, diagnostic check the residuals. Is it a white noise process? And if passes all the diagnostic checks, we then proceed to produce forecasts for the data. So I'm going to use this simple example, Australian electricity production. Again, if I use the autoplot function, I can get this particular graph. So we need to notice that you can see somewhat of a linear trend. We notice that there's a seasonal pattern as well. All right, notice that the peaks and the troughs, it repeats after regular intervals of time. So there is seasonality as well. So we need to make sure that we account for the trend. We need to make sure that we account for the seasonal pattern as well. So visualizing the data is very important in any time series forecasting exercise. So a possible linear regression model that accounts for these two behaviors is this particular model here. This is your dependent variable, anchored intercept. All right, this is the trend variable that is meant to account for your trend. And because this is monthly data, I'm going to have 11 dummies. All right, D2, D3, D4, D11 to D12. So this is a dummy for the month of February. This is the dummies for the month of March, for the months of April, November, and December. So January is the omitted variable, it's the omitted dummy variable. That's what I call our reference dummy, our benchmark, or the base variable. All right, so we can fit this particular linear regression model in R quite simply. All right, now if you were doing this in R in Excel, it's going to be very troublesome because you've got to create 11 dummy variables. All right, and then you've got to put 0 and 1s and 0 and 1s, which is very annoying. But in R, thank goodness, it's very easy. We only need to use the TSLN function. All right, I think some of you might be familiar with the LN function. LN function R is just a linear model. The TS just stands for time series. All right, times the linear model. So I just call the data set. All right, I regress it against a trend and season. I do not have to create any new variables. I don't have to create a variable called trend. I don't have to create a variable called season. It's basically telling R, I want to include the trend variable and I want to include seasonal dummies. And when you put it through the summary function, all right, you get all your results here. All right, so this is your intercept, all right, your trend, right? This is your estimate for February. So in this case, I'll have beta 2 hat, which is minus 648, and then beta 3 is equals to 233. So how to interpret this? We basically says that, February has a lower electricity production than January by 648 megawatts. All right, this electricity production. Beta 3 hat is positive. Again, January is my reference point. So I would say that electricity production in March is 233 megawatts higher than that produced in January after adjusting for the trend. All right, and then let's say season 4 minus 496. So beta 4 hat is minus 496. Because it's a negative value, it means that electricity production in April is actually lower than that in January. So we interpret this as electricity production in April is lower than that of January by 496 megawatts after adjusting for the trend. Okay, so this is how you interpret it. So to do this R, it's really, really easy. All right, I'll create my data set, elect 2. Okay, use the autoplot. This is the data set I'll get. So I'll just use the TSLN function here. All right, regress my data set, elect 2 against the trend and season, and I just save it into the object name fit.elect. Okay, and then print the summary. I have the results here that we saw on the slides. Okay, so it's quite straightforward to run linear regression models using time series data using the FPP2 package. Now, we need to go to the diagnostic check. We need to make sure that the estimated residuals are a white noise process. Is there a way to make another point as a reference point? Yes, there is. All right, that you can definitely do it, but you need to then adjust the data frame where you need to adjust what your reference point is as February or March or April. So by default, R would take the first season to be the reference point. If you don't want that as a reference point, you can actually change it. All right, but that happens in the data preparation part. It does not happen in TFs or in function part. It has to happen in your data preparation part. Okay, so we need to ensure that the residuals are a white noise process. So the function that we use is actually quite straightforward. It's a check residuals, all right? It's very intuitive. All right, let me check my residuals. And the argument that you put in here is the name of the regression model that we saved as fit.elect. And you get two sets of output. The first set of output is this graph here. This is the time series plot of the residuals. This is the ACF. And this is a distribution with a normal density overlay over it. All right. So what we hope to see is an ACF, which is mainly between the two 95% confidence interval. All right, between the 95% confidence, because this indicates that there will not be any white noise process. The second output you have is the Bridge-Godfrey test or serial autocorrelation. Oops, sorry. And what we are really interested in is here is the p-value. So your null hypothesis would be no autocorrelation in the residuals, and your alternative hypothesis is there is autocorrelation in the residuals. In this case, my p-value here is greater than alpha, so I do not reject the null. All right, I do not reject the null. This means that there's no autocorrelation in my residuals. It's white noise. It has passed my diagnostic test. So to do this in R, all right, I can use the check residuals function. If you put test equals to false, it just means it just shows you the plot. If you put plot equals to false, it means it just shows you the test results. So if I just type my check residuals fit.elect, all right, by default, it gives you everything at one shot. All right, you get the plot over here and you get the test results over here. Okay, so very straightforward in doing diagnostic checks for a regression model. So how do I then produce forecasts using a regression model? Straightforward, I just use the forecast function. Right? Just take the model name that you have. All right, in this case, I save my estimated model as fit.elect. I pipe it into the forecast function. And then you specify how many periods do you want to produce forecast for. In this case, I say, let's produce 24 steps for 24 periods of forecast. And I plot the function. And this is the forecast that I have. You have by default, it gives you the 80 and the 95% prediction intervals. So notice how the forecast here looks quite sensible. It continues the upward trend and the seasonal pattern. Okay. So to do this in R, again, you can just take the fit.elect model that we have, pipe it into the forecast function. All right, specify 24 periods. If I do this, then you get the point forecasts. All right, the point forecast for the next 24 months. This is the 80% prediction interval and the 95% prediction interval. All right, if you want to plot it, then you pipe it into the autoplot function. All right, and you get the forecast produced over here. All right, so I've always find that time series forecasting, the theory is more difficult than practical. All right, later on, the codes, as we progress on, the codes are actually quite straightforward to do. All right, so this is regression. Now, what if there's a non-linear trend? All right, so let's say this is Boston Marathon winning time. So this is annual data. Okay, so this is annual data. So there's no possibility of a seasonal pattern. All right, there's no seasonality in annual data. All right, so I can take the data set marathon, plot it. Notice that there's a slight, kind of, I can't really draw too well here. I hope you can see that there's that slight kind of non-linear trend. Now, this function here means I'm just going to fit a linear trend. All right, just regress marathon against a trend and save it as fit.lin. If you do that, this is what we have. All right, you can clearly see that this is not a good fit. Right, this is not a good model to have to produce forecasts. because it does not capture the nonlinearity. So this is the residuals from the regression model. Notice that you have this kind of quadratic shape. So this is definitely not a good fit because your residual still displays some kind of pattern over here. So what we could do is to add additional regressors. All right, we could use what we call a piecewise linear trend where you add regressors. All right, you have one regressor that models that time variable. You add a regressor that takes on two values, 0 for all the years before a nominated time point, and t minus tau for all the years beyond this time point tau. All right, so this is tau. Now, what is tau? Tau is basically the point in time at which the line should bend. So this is specified by the user. All right, so when I fit a piecewise linear trend which bends at some point in time, the non-linear trend can be constructed via a series of linear pieces. All right, you construct a series of linear pieces as we'll see later on. All right, so beta 1 would be the slope of the trend before that time naught. Beta 1 plus beta 2 will be the slope of the trend after time naught. Okay, so what we have here is I have over here, this is the standard linear regression model that we saw earlier on. Right, I fit a linear model and I produce a forecast, a 10-step ahead forecast, and save it as forecast.lin. Now, we've seen that it's not a suitable model because my residuals don't look good. So I can try a piecewise linear trend. All right, in this case, I'm going to introduce two time points, 1940 and 1980. All right, which means I'm going to introduce a break here, 1940 and 1980. Sorry, this is the actual data set. Right, 1940 and 1980. Okay, we will see how the piecewise linear trend looks like later. Okay, so this is my time trend variable. This is T1, this is T2. All right. So this is like my X1 variable, this is my X2 variable, and this is my X3 variables. So notice that this is basically T minus tau 1, and this is basically T minus tau 2, which is basically what we have here. All right. T minus tau is either 0, T minus tau. So how we create this variable is by using this function Pmax. All right, and this TS is just meaning I'm going to create this variable and make it convert it into a time series object. All right, so Pmax is the mathematical function that we saw. TS means I'm going to create the resulting variable to be a time series. And all we need to do is just, again, use the TSRN function, regress marathon against these three X variables, and save it as fit.pw. So going back to R over here. All right, these are my linear model. This is the piecewise linear trend. Okay, I'm going to create the three time variables. So just to show you how it looks like, this is the variable T. All right, it's just the year from 1897 to 2016. This is what T1 looks like. It's 0 before 1940. After 1940, it starts having values here. T2, it takes a value of 0 before the year 1980, and it starts taking values after 1980. All right, so 1940 and 1980 were the two time nodes that I had specified earlier. Run the regression. All right, and if you put a summary, all right, you get the standard regression model. Okay. Now let's produce forecasts. Okay, so I'm going to create the three new variables for the 10 time period. So when we want to produce forecasts for a piecewise linear trend, it's a little bit more work for us because you basically need to create the values of your X variables for the forecast period. All right, you need to manually create the values of the regressors, the values of your X variables for the forecast periods. So this is what I'm doing over here, t.new, t1.new, t2.new. All right, creating the values of those three X variables for the next 10 years. Save them as a new data format, and then I produce a forecast using the forecast function. Okay, so I use the forecast function, call out the object name, and I need to specify the new data. What are the values of the X variables for which you want to produce forecast for Y? Okay, so I produce a forecast here, and if I proceed to plot it, I get this very nice plot. All right, so this red line here is that linear regression, just one straight slope. Doesn't look great. But with piecewise linear regression, notice that I've got three types of trend. All right, I've got the first trend over here, and then the second one, which is steeper, and then the third one, which is flatter. All right, and then these are my forecasts from the piecewise linear trend, and this is the forecast from the linear model. All right, so I think we can clearly see that the forecast from the piecewise linear trend, it looks more sensible. All right, the forecast from piecewise linear trend, it looks more sensible. So this is the non-linear trend, all right, using a piecewise linear approach. We can definitely use splines as well, but I'm not going to cover that in this particular talk. Okay, again, you can go through some residuals check, all right, using the check residuals function, all right. I won't go through them. Okay. Now, exponential smoothing is a very popular method as well. Now, there is actually a progression here. Regression models work perfectly if your data set has a linear trend. If your data has a non-linear trend, well, we could consider using piecewise linear trend, where you have a series, where you map series of linear trends to map out a non-linear trend. But if the behavior of your series, the trend behavior changes quite frequently, then it's probably not wise to use the piecewise linear trend method. Probably not wise to use a piecewise linear trend method. We might want to use something called exponential smoothing. So exponential smoothing actually became very popular in World War I. All right, it became very popular in World War I, and basically it's based on the extrapolation of past patterns. And it was a very simple method to use because it just consisted of forecast equations that you could simply update and maintain in the database. It's like a simple automation. You have just type in one formula in the Excel cell. As you enter new data into subsequent rows, the forecast will update itself because of that formula that you've already keyed in. And it basically captures three things: the level, the trend, and seasonal factors. Now, exponential smoothing, what does the name actually mean? Smoothing actually means average. All right, I'm taking an average. Exponential just means I'm doing a weighted average. All right, so exponential smoothing really, it just means a weighted average of past observations where the weights decline or they decay exponentially as the observations get older. All right, intuitively, you would think that the more recent observations should have greater weightage in producing your forecast. And observations that you observe very far distant in time, they should have a lower weightage attached to the forecast that you're trying to produce. All right. So exponential smoothing has three things. You need to calculate the level, trend, and the seasonal index if there's a seasonal pattern. Now, there are actually, if you consider variations in the combination of the trend and seasonal components, you have 15 possible exponential smoothing methods. And I would like to emphasize the term methods here, because later on I'll be talking about the difference from models over here. So this is exponential smoothing methods, and it's labeled by TS. T is the trend, S is the seasonal component. So if I say AM, then I'm saying that I'm having additive trend and multiplicative seasonality. If I have MN, then I'm saying I have multiplicative trend, and the N means no seasonality. So these are the options that I have. I can have no trend, additive trend, or additive damped trend. The damping here means that sometimes practically or intuitively, it doesn't make sense for the trend to continue indefinitely. All right? It doesn't make sense for the trend to continue indefinitely. Sometimes it makes sense that, maybe a while into the future, we should kind of taper that trend off. All right? And that's what the damping effect does. It tapers off that trend. In terms of seasonal component, I've got three options: no seasonality, additive seasonality, or multiplicative seasonality. All right. So these are some of the very common exponential smoothing methods that were developed in the 1950s. And this will be the mapping to the various TS classifications. Okay. Now, in the early 2000s, Professor Rob Hyman developed something called ETS models. Now, The biggest problem with the exponential smoothing methods is they were not able to produce prediction intervals. It could only produce point forecasts. So in about early 2000s, Professor Rob Hyman developed exponential smoothing models that actually allowed for the calculation of prediction intervals in addition to the point estimates. And some of you might be familiar with state space models. So the ETS models are actually state space models. All right, for each of the methods, you have two possible models, one with additive errors and one with multiplicative errors. All right, so you have what we call the ETS model that stands for the error, the trend, and the seasonal. So you call it additive error or multiplicative error. All right, so these are the equations associated with the ETS models. Don't have to worry about them. The theory is complex, but the practical is actually quite straightforward. All right, so these are the equations. So the forecast equations are actually computed from all these equations here. All right, so these are the math behind how the point forecasts are calculated. And then these are the equations for those with multiplicative errors. Okay, so to estimate exponential smoothing models in R, I only need to use the ETS function. It's that straightforward. Okay, so if I just go to exponential smoothing, okay, R will automatically choose the exponential smoothing method for us. So in this case, it returns MAD, which means multiplicative error, additive damn trend, multiplicative seasonality. It chose this model for us. Okay, you can definitely specify a model that you want. So if you put model equals to AAA, which means you're specifying a specific exponential smoothing model. Okay, but in practice, we normally just let R choose the exponential smoothing model for us. Okay, and how it does is basically it chooses a model by default using the information criteria. It will choose a combination of the error and trend and seasonal component that minimizes the Akaki's information criteria, or AICC here means it's the corrected Akaki's information criteria, or the Bayesian information criteria. So there's a lot of things going under the hood, but in practice, just use the ETS function. All right, if you want to produce forecasts, all right, so let me show you how good this data actually is, this model is. Okay. So over here, all right, I fit it into ETS function and I shall save it under this name ho2.ets. Okay, and what I'm going to do here is I'm going to plot the original data. All right, I'm going to plot the original data. I'm going to add the fitted values. Okay, I'm going to get this is the model that I had. I'm going to extract the fitted values and I'm going to overlay it on my original data set. So notice how well the ETS model performs over here. It overlaps the actual data sets quite closely. It aligns itself quite closely. All right. So if you just try imagining using a linear regression model, is not going to get such a good fit. All right. Because the exponential smoothing model, it's based on past observations and it attaches, it's like a moving weighted average. It attaches weights to past observations and it's this automatic feeding and updating of information. So this is a very good fit of the data set using exponential smoothing. And if I want to produce forecast, again, just use the pipe operator, all right? Data set, pipe it into the ETS function that will fit the model, produce the forecast, and get the auto plot. And then this is the forecast that you get from exponential smoothing. Okay. So all this is just the details behind the codes. I'm not going to go through them. I've included them just for presentation purposes. Now, let's go into ARIMA models. Now, I've broken up ARIMA models into two parts, the non-seasonal and the seasonal ones. So they are a very popular class of models. Now, exponential smoothing models that we saw earlier on, it basically describes trend and seasonal patterns in the data. ARIMA models is different. It doesn't really pay too much attention to trend or seasonality. ARIMA models actually models autocorrelations in the data. And that's why earlier on, I had to introduce the concepts of autocorrelation and partial autocorrelation, because ARIMA models look at these two things only. They look at autocorrelations and partial autocorrelations and label them. And therefore, identification on these ARIMA models it relies heavily on the sample ACF and PACF. So I'm going to introduce various components of the ARIMA class, what the statistical properties are, and how do you actually identify them. Now, this is a very quick introduction. I actually take 3 weeks to cover ARIMA forecasting in my classes, so I've got less than that. So let's break it down. ARIMA, AR, I, and MA. So the AR stands for auto-regressive model. One here basically means, so a model is auto-regressive if you have the lag of your dependent variable as your regressor. All right. So YT here is my dependent variable. If the lag of it as a regressor, in this case YT minus 1, it's called auto-regressive model. It's called order 1 because I only include one lag of it. All right, I only include one lag of it. So these are mathematical formulas. In practice, how do I identify an AR1 model? This is the key thing. An AR1 model is good for your time series if you notice that the ACF has an exponential decay and if the PACF goes to 0 after lag 1. All right, these are derived from mathematical properties that I don't have time to go through. Okay, so here's an example. This is an AR1 process. All right, one lag, 0.7. This is how it looks like. It looks stationary. So notice my ACF declines exponentially. And look at my PACF. This is lag 1. It's significant at lag 1. And then notice beyond that, beyond lag 1, all my partial autocorrelations are equal to 0. So what does this mean? If you take a data set, you plot this ACF and PACF, if you notice such a pattern, then you can make an intellectual guess saying that, hey, maybe for this particular data set, AR1 is the underlying data generating process. Okay? So exponential decay in the ACF and the PACF, you have the significant autocorrelation at lag 1. For a stationary AR1 process, phi must be less than 1 in absolute value. So if let's say you have a coefficient greater than 1, you have an explosive series, right? Notice how the series just goes to infinity very quickly. So we've got to make sure that the absolute value of phi is less than 1 for AR1 process to be stationary. ARP means I have up to p lags of the dependent variable as my regressor. So this is an ARP process. How would the ACF and PACF model look like? How would the ACF and PACF of ARP look like? It will look like this. Your ACF also have an exponential decay. The PACF cuts off to 0 after p lags. All right, it cuts off to 0 after p lags. So for example, I've got an AR2 process here. So in this case, p is equals to 2. Right, I've got the first lag, the second lag. So notice how my ACF decays exponentially. Notice how my PACF significant at lag 1, significant at lag 2, and beyond that, all my partial autocorrelations are equals to 0. All right, so if you have a time series that shows the ACF and PACF like that, again, we can make an intellectual guess that says that, hey, this could be an AR2 process because I see an exponential decay in my ACF and my PACF is significant at lag 2 and 0 beyond lag 2. So this is an AR2. MAQ, moving average process, is where you have your error terms, lags of the error terms as your regressors. So this is the model error term and these are the lags of the error term. All right, and these are all regressors. So notice that they have coefficients before them. How do you identify them? My PACF will have the exponential decay. My ACF goes to 0 after lag Q. Again, everything is based on the ACF and the PACF. So here's an example. I've got MAQ, MA2 here. So Q is equals to 2. Notice how my PACF, exponential decay, my ACF, significant at lag 1, significant at lag 2, and then it's 0 beyond that. Okay, so if you have a time series where you have the ACF and the PACF that behaves like this, you can make an intellectual guess that this is an MA2 process. So notice the difference between the behavior of ARP and MAQ. For AR process, the exponential pattern happens in the PACF and the cutting off happens in the PACF. For the MA model, it's the reverse. The exponential decay shows up in the PACF and the cutting off happens in the ACF. Now, if I mix the two together, it's what I call the ARMA process. So this is an ARMA PQ where I've got P legs of Y and Q legs of the error term. So notice I got P legs of the dependent variable and up to Q legs of the error term. So this is an ARMA PQ when you mix them together. And this is how it is in the backshift notation. All right, remember that BYT is just YT minus 1, or BET is just equals to ET minus 1, is the effect of shifting the time series back by one time period. Okay. Now, ARIMA, all right, I have this additional term here. So this looks like an ARMA process, but notice that it's not Y, it's all these Y primes. I have all these primes appearing. So Y prime T is basically 1 minus B raised by DYT is basically the ARMA model with differencing. All right, the differencing happens to your YT. Okay, so if D equals to 1, then the Y prime T here is just really YT minus 1, which means you are modeling the change in YT. All right, if D is equals to 1, then you're modeling Y prime T, you're modeling the change in YT. Okay, so we always denote ARIMA models using P, D, and Q. P is your autoregressive part, D is a degree of first differencing, and Q is a moving average part. All right, and differencing is to help us stabilize the mean. All right, this is how it looked like mathematically. I'm going to skip it due to time. Okay, now how do you produce forecasts using ARIMA models? All right, now I don't have time to go through the details, but you can refer to this link over here. I'm going to use the automated function. I'm going to use the auto.arima function that helps us select the ARIMA process automatically. All right, and there are just 3 steps. Plot the data, transform the data if needed to stabilize the variance. So you could use a box-Cox transformation, or you can use a log transformation, and then you could use the auto.arima function. So in this case, all right, I'm going to use the Lake Huron. All right, so it's a lake. All right, this is again annual data. I could just use the auto.arima function, call the data name, and if you really want a detailed run, all right, if you really want a very detailed and very computationally intensive to make sure it goes through a grid of values, a grid of possible parameters, we will specify stepwise approximation to be false. Okay, run through that, and it identifies the ARIMA 211 model for us. All right, it's quite quick. All right, so in this case, 2 legs of the autoregressive, 1 degree of differencing, and 1 leg of the error term, and this would be our coefficient error terms. Now, these coefficients have no econometric interpretation meaning. All right, it's not like in regression model, beta 1 is the change in y as x increases by 1 unit. In ARIMA models, these coefficients have no economic meaning. All right, no economic meaning at all. I can go through a diagnostic check, again, using the check residuals function. Okay, looks quite good. It looks like a white noise process. My ACF are all within the bounds. All right, if I get the drum box test, my p-value here is 0.825. So it means that, hey, this ARIMA 211 seems to be quite a good fit. And then if I want to use forecasting, that's straightforward. Just again, use the auto.arima function, pipe it into the forecast function, specify how many periods you want to forecast. In this case, I want to forecast 10 periods ahead, and you plot the forecast. Okay, this is the forecast that you have, a very wide prediction interval over here. Now, in time series forecasting, and I don't have time to cover this, there's actually attention needs to be paid as well to the prediction interval. We need to actually ask ourselves, are prediction intervals sensible? But I won't have time to cover that in this particular case. I'll just focus on the point forecasts. Okay, so these are the codes that I saw, pass the residuals check, and then just really making use of the forecast function, which is very handy in producing forecasts. Now, seasonal ARIMA models is used for data with seasonality. And this requires us to add 3 more terms. The seasonal AR, the seasonal differencing, the seasonal MA, And the M over here is basically your seasonal frequency. If you're dealing with monthly data, M is equals to 12. If you're dealing with quarterly data, M is equals to 4. Okay, so this is the math of how you write certain ARIMA models, right? But how do you identify them? So this is a seasonal MA1, right? In this case, this is Q equals to 1, and in this case, P equals to 1. The most important thing here is to only pay attention to the seasonal lags of the PACF and ACF, which means I look at my ACF, I look at PACF, I observe what's happening at the seasonal lag. So if I'm dealing with monthly data, I look at what's happening at lag 12, lag 24, lag 36. I don't care what's happening at other lags. If I'm dealing with quarterly data, at M equals to 4, then I'll pay attention to what's happening at lag 4, lag 8, lag 12, and lag 16. I won't pay attention to any other of the lags. Okay? So for seasonal MA1, I will have a spike at lag 12 in the ACF. So again, this is assuming that you have monthly data. If a lag 12 in the ACF, the PACF exponential decay in the seasonal lags only. Okay? For seasonal AR1, you have an exponential decay in the seasonal lags of the ACF, and then you have a single spike at lag 12 in the PACF. Okay, so the principle is the same. For the AR model, the spikes is in the PACF, the exponential decay is in the ACF. For MA model, the spikes is in the ACF, exponential decay is in the PACF. All right. So here's an example over here. All right, some drug sales over here. I take a log transformation to stabilize the variance. So this is the data set that I work with, all right, the LHO2. I'll need to take a seasonal difference. I'll need to take a difference to stabilize the mean. All right, so this is if I'm really doing a manual fitting of the ARIMA model. All right, to save time, I'll be sharing these slides with you, so don't worry. All right, I'm just going to go straight into the auto.arima function. All right, you could use the auto.arima function, call out the data name. Lambda equals to 0, this corresponds to my log transformation. All right, the log transformation is to stabilize my variance. All right, is to make sure that my variance is constant. All right, and I'll save it under the auto fit. So if I go to my codes over here, all right, so I use the auto.arima function, call out the name, specify lambda with 0 means I'm going to do a log transformation. All right, save as auto fit. All right, so it identifies the ARIMA 211012. All right, and these are the coefficients. All right, this is a seasonal moving average 1, seasonal moving average 2. This is a non-seasonal MA1, and these are the non-seasonal AR coefficients. If I check the residuals, all right, looks quite okay. All right, most of the sample autocorrelations are within the lags. Within the 95% prediction interval. Okay, and if I do the John box test, p-value is 0.17, so I will not reject the null, which means that, hey, this ARIMA model has fitted the data quite well because the residuals have no autocorrelation. And if I want to forecast, just use the forecast function again, and then you can plot the data. Right, and this is what we have. All right, it looks quite good. It contains that seasonal, continues on that seasonal pattern. Okay, now, unfortunately, I think I've run out of time, so I won't be able to go through bootstrap bagging. Again, this is actually quite a new thing in time series forecasting. Bagging is like, in cross-sectional data, bagging is very, very popular. Or you might have heard of random forest. Random forest is basically a type of bagging, all right, which is bootstrap aggregation. So it's not until recently where someone developed an algorithm to actually do bagging for time series data. All right, so I won't go through it. Now, I'll just very quickly, maybe just next 3 minutes or so, we have gone through a lot of forecasting models, regression model, piecewise linear regression models, exponential smoothing models, ARIMA models, and bagging. How would you decide which one is the best? Which one should we use? Basically, we should use the one that gives you the best forecast accuracy. All right. So The traditional approach is this, and I think you might be familiar with it for those who do data science. You basically have a training set data and the test set data. Your training set data is about 70%, test set is about 30%. All right. And then your training set data is used to develop a model, estimate your parameters. You do not touch your test set at all. All right. So the whole idea is you take the training set data, fit a model, estimate the model parameters, and you produce forecasts for the test set. Right? You produce forecasts for the test set, and then you compare the actual values in the test set with the forecasted values for the test set that your model produced. All right, and then you summarize these forecast errors to develop a measure of forecast accuracy. All right, so this is what we have here. All right, so let's say this is YT plus 1, YT plus 2, and then this is 1, 2, 3, 4, 5, 6. This is YT plus 6. All right, so let's say your test set data has 6 observations. What you do is you take your training data, you fit some kind of model, you produce your forecasts. Y hat T plus 1, Y hat T plus 2, Y hat T plus 3, all the way to Y hat T plus 6. What you then do is to get your forecast error. All right, you get your E hat T plus 1, E hat T plus 2, E hat T plus 3, all the way to E hat T plus 6. And what we want to do is to obtain a summary measure of these error terms. The method and the model that gives you the smallest measure is the one that is the best forecast accuracy. All right. All right. So this is what we have here. The forecast error is the difference between your observed value and the actual forecasted value. So over here, there are some measures, the mean absolute error, mean squared error. All right. You might have heard of them. Root mean square error and mean absolute percentage error. All right. So I've got an anti-diabetic drug subsidy here in Australia. I use 2 forecasting methods here, the ET exponential spooling models and the ARIMA models. All right. So you can see that this is actually my test set. All right. This is my test set. This is my training set. All right, and I produce forecasts for the test set period using the ETS and the ARIMA models. And what we want to do, this is how we do it. First, we create a training set data. We just use a window function. So take your whole data set, and specify a cutoff point. So in this case, my cutoff point is in June 2006. This is my training set data. My test set data would start from July 2006, all right, using this window function. Then I'll use the training set data. All right, I use the training set data to fit my model. So in this case, I use 2 possible models: the ETS model using the ETS function, and the auto.arima function correspond to ARIMA models. And what we then need to do is use the accuracy function. So the accuracy function helps us get all these measures: the MAE, RMSE, MEP, MESE. All this is computed automatically for us using just the accuracy function. So the theory is complicated, but the practice is really easy to use in R. So this is, all right, the first argument is basically your predicted values. And then the second argument is to specify your actual test set values. So that's all you need to do. And this is the result that you get. So notice that the ARIMA model is more accurate because it has the lowest RMSE, lowest MAE, lowest MEP, and lowest MESE. All right, we are looking for the model that returns the lowest measures. Okay, the modern approach. All right, now notice that in the traditional approach, I only have 1 test set. This is a traditional approach. Now, the modern approach is cross-validation. So cross-validation is very popular in the cross-sectional dimension. Time series, we are now able to do time series validation. So what we have in time series cross-validation here is I now have multiple test sets. Previously, only 1 test set, but with time series cross-validation, I now have multiple test sets. The red dots here represent my test set. So I'm able to get a lot of my forecast error over here. All right, all these would be my 1 step ahead forecast, and then this would be correspond to the first one, this would correspond to the second one, the third one, the fourth one. Okay. So the forecast accuracy is computed by averaging over the test set. Okay. This is if you want to evaluate the forecast accuracy of, let's say, a 4-step ahead forecast. Okay. So the time series cross validation here is very flexible. You can actually evaluate forecast accuracy to see which models can produce accurate 4-step ahead forecasts. 1 step ahead, 2 step ahead, 3 step ahead, up to you. And the function to use is really just TSCV, time series cross validation, and you just compute the root mean square error term here. Okay, so I'm sorry that I have to rush through because we have run out of time. Okay, but I see in the question here, there's one to go through the bootstrap and bagging methods. So very quickly, the bootstrap and bagging methods is this. It basically means this. The black line here is my original data set. What I want to do is to so-called create multiple possible data sets. So what I have here, the black line represents the actual data set. The colored lines are the possible permutations, replication of the original data set. So in this case, I've produced 10. All right, I've produced 10 possible other time series data set. What I then do is produce forecasts for each of the time series data sets. All right, I produce a forecast for each of the time series, and then I average those forecasts. Okay, so this is the idea of bootstrapping, right? You have your original data set here. You take these sets of bootstrap samples. So in this case, I create B number of time series data sets. I produce forecasts, all right, for each of these data sets, right? I then take the average of all these forecasts to get my overall forecast. So that's the whole idea behind bagging. And to do that in R is really, really straightforward. It's just, if you want to use exponential smoothing, we just use the back ETS function. So this is the data set. You pipe in the back ETS function. What this does is it creates 100 possible time series data set. It fits exponential smoothing to each of those 100 time series data set. It produces 100 sets of forecasts. And it takes the average of those 100 forecasts to just give you one final forecast. So it's computationally intensive, and it might take a while before results are actually produced. All right, if you want to use the auto.rima function, we use the bag model function and specify the function to be auto.rima. So what this does is, takes a data set, or if you pipe it into the bag model function, it creates 100. By default, create one. If you want to create more than 100, you can, but by default it's 100. It creates 100 time series data set. It fits an ARIMA model to each of those 100 data sets. And then when you pipe it into the forecast function, it produces forecasts for each of those 100 models that you already have, and then it averages it out. So this is bagging. Okay. I think that's all. I've run out of time, but I hope this is really a crash course. I'm so sorry that I have to rush through, but I just wanted to expose all of you to as much, knowledge and methods as possible. And of course, if any of you are interested for me to, go to your place to do a workshop, do a one-day workshop, any of this, I'm more than happy to do so. All right. But this is very, very brief crash course introduction to time series forecasting. And all right, back to you, Kim.
Right. As always, Jason, you have been excellent.
Thank you.
Amazing. So I must say, very clear, and your presentation is very organized, as always. And I've read a few books on time series and follow a few tutorials on time series. I think your talk may be the easiest one to follow.
Yeah, because actually, I actually focus on the narrative. I think we should not see them as separate models, but these models have been developed as an evolution of it. And of course, there are more advanced forecasting ones, such as the bagging ones. Yeah.
Yeah, true. I wish we have more. We have more time, but but unfortunately we don't have
Yeah.
that privilege. And Jason, you are on LinkedIn, right? So just in case
Yes,
anyone wants to connect with you, and we are, looking forward for collaboration with you, Jason,
Sure. I'm
on
open.
a much bigger scale to beyond what we are doing now. And yeah, again, it's amazing talk by you. It's not easy, I think, to cover the whole models in time series and forecasting, but you managed to do so, and very clear. And I really appreciate that. And I think on behalf of the our school, the School of Medical Sciences, I would like to say thank you very much, Jason. We have people from, I think, from Sunway, from our medical schools, from Ministry of Health, and I think time series data. We have lots of time series data, but underused, and because we don't have that skill. So I think with your expertise and your help, I think we can do more with this sorts of data. And
Yeah.
so, Jason, I hope you get well soon. I hope
Thank you.
get well soon. Even though with your 70%, voice, you still manage to present very well. So thank you again, and to all participants, thank you for attending, and I wish you all the best and enjoy. Have a nice day, everyone.
All right. Thank you so much.